I will start within 2 minutes. Hi, good morning, everyone. I am audible. So can anyone please respond? I am audible. My voice is clearly audible.
Yes, yes, yes.
Okay. Screen is visible to everyone.
Correct. Invisible.
Thank you, everyone. Yeah. Good morning, everyone. So I myself Satish. So I'll be taking the today's session. So that is a demo on design for testability. So myself, CEO and the lead trainer for DFT at VLS Summits Bangalore. So today's agenda for today's discussion follows as like this. So that is, let us start with what is the VLSI design flow. So and next where we'll get the DFT part, and let us go deep into the DFT. So DFT, introduction to DFT, what we do in DFT, and what is the flow we follow in DFT, and the tools we use in the industry. In part of the DFT is the scan insertion. So let us discuss about the scan insertion, scan compression, and ATPG and simulations. And on the non-technical side, so also we'll cover some of the topics. So you may be not aware about what is DFT. Some of you may not be familiar with what is the DFT. So let us go with why we need to take a DFT training and what skills we should have to get the opportunities in DFT industry, in the DFT, about our institute, that is VLSI Minds, and let us talk about what are the latest trends in DFT and what opportunities we have in the VLSI domain. So this is all about, this will be the agenda for today's discussion. Yeah, I would like to thank each and everyone for showing interest in joining today's demo session. So let us begin with this. Yeah. So I hope all of you are from the background of electrical sciences, maybe from ECE or EEE branches. So you may be familiar, but so in the industry, how it works, the VLSI design flow is the broadly classified into two different classes, that is full custom flow and semi-custom flow. So what we do in full custom flow is, so we do everything from the scratch, means we will start from the scratch. So it will be at the transistor level. So we have to do the schematic, we have to write the layout, we have to bring up the design. So that is what we do in the full custom flow. Whereas in the semi-custom flow, so again, we have broadly classified into two classes, that is ASIC design and FPGA. So you may be familiar with the FPGA because in the most of the academics, it will be covered with the FPGA kit, and the VLSI design will be practiced with the FPGA kit, correct? So whereas in the ASIC design flow, it is totally different from the FPGA. So it is application specific integrated circuit. So this flow whatever the ASIC design flow we follows for a to design an IC, which we need to get the chip for a particular applications. Just like, for example, you wanted to have a mobile chip. So the mobile chip can work only for a mobile applications, right? So similarly, laptop chip, if you are designed, it will work only for the laptop applications. So whereas a FPGA, so you can program it as per your requirement. So that means, so you can change the program whatever you wanted to do. So you can dump the program on the hardware which is already existing, and then you can analyze the performance or whatever about those particular system. So in the ASIC design flow, so we actually start from the gate level net list. Means we do it at the gate level. So that means that, so most of the 85% of the companies in the VLSI industry go with ASIC design flow, where we need a mass production. So that means that, for example, I need to design an IC which has to be placed in the automobiles. So automobiles, let us assume we wanted to make a driverless car or autonomous driving car. So on that, if you wanted to make a chip, so that cannot be produced with one or two. So it has to go with a bulk production. So that is mass production. During that time, we should go with ASIC design flow. So as cost involvement is totally different in both the designs, both the ASIC and FPGA. So based on the requirements of the industry, so they choose either ASIC design flow or FPGA. Usually, the most of the companies who works for automobile industry or communications, like mobile chips or laptop chips, all these will go with ASIC design flow. Where the companies who works for the defense applications, where we have a limited number of products to be produced, there we can go with FPGA. So this is what the clear understanding of how the VLSI design flow goes in the industry. So let us get into the, so anyway, we comes under the DFT engineers, we comes under semi-custom flow, that is in the ASIC design flow. So let us get into the, so briefly let me explain you what is a full custom flow and semi-custom flow, and then later we'll go into the DFT flow. So yes, my voice is clearly audible for everyone. So if I am going fast or slow, let me know so that I can correct it now itself. So all of you are able to catch me. So please respond. So let it be more interactive.
Yeah, Satish, you are going slow. Good. Go like this only.
Thank you.
I think I'm getting.
Yeah. So this is the full custom design flow. So yeah, where as I mentioned, we have to start from the scratch. So that means design specification. So the customer will give the design specification. According to that design specifications, we have to write the schematic. So after writing the schematic, we have to simulate it. So that is pre-layout simulations. We have to verify that design. So if it is meeting with the specifications, so then we'll just go ahead with that. So if it is not meeting with the specification, then again we go back to the in the schematic, so that it should meet the specifications which are required by the customer or to make that particular design. So if it is met, then we'll go for the layout design. So we draw the layout, verify that for the DRCs and any violation that will be solved, and then it will extract the parasitic extraction. We go for the forced layout simulation. If it is failing or if it is not our specifications, then we need to correct it either at the schematic level and as well as at the layout level to meet our specification. If it is met, then GDS extraction will be extracted. GDS will be the GDS2 will be the output, and it will be given to the fabrication for boundary. So how it looks, that is schematic equivalent symbol for an AND gate. So this will be the schematic which we need to write to the specification, and then we have to meet our requirements, and then we have to write the layout. These all will be done at the scratch level, means from this transistor level. Everything will be done at this transistor level. So that is this is a specific means specification driven. So that is meet all the design requirements. So iterative flow. So that is, it will be continuously checked and verified. So it will be checked and verified continuously for all the at all the stages, both at the free layout stage and as well as at the post layout stages. And it will be in each stage we will be checking all the DRCs. And then we, as a main requirement or goal is to get the good quality output, that is GDS extraction, which will be sent for the foundry, so that we'll get the more reliable and efficient manufacturable chip output. So from the custom means full custom wise. So mainly here what we do is the analog IPs or analog designs. So more focus by using full custom. The full custom designs will be done for the analog devices, means analog designs. So, and also to make the standard cells like AND gate, NOR gate, or whatever the gates, buffers, inverters, all these are required for the later on when we have a standard cells we call in the industry. So those standard cells also will be designed by the full custom design flow. Okay. So I request, if you have any doubts at any stage, please unmute and ask at any stage. So next, when we get into the ASIC design flow, as I mentioned in the semi-custom flow, so one of the design method is ASIC design flow, and another one is FPGA. So let us move mainly concentrate. We'll concentrate on ASIC design flow, because as DFT is a part of ASIC design flow, so we'll go with this. So ASIC design has different stages of designing an IC. So just like for example, we wanted to plan constructing a house. How do we plan? So similarly, when you wanted to come up with an IC, when we have a plan to bring up the chip into the market, we should undergo so many stages. So all these are the main stages which we need to undergo to bring the chip into the market. So that is starts from chip specification. So that has to be given from the customer. According to the customer, will be having a system architect or chip architect. He will give the all the number of, means how many number of blocks should be there, all those things in detail I will take up in the next slides. So design verification team will come, and then synthesis team will come, and then partitioning the entire chip or the entire IC into different parts, because the entire IC cannot be taken at the same time. So because the partitioning will be make easier to test the chip at the different levels, so that will be done at the partitioning of the chip. And then the DFT insertion will come. After that, the backend team will come. The backend team, that is the PD process will start. That is for planning, placement, CTC, and routing, and final verification will be done. That is physical verification, and GDS will get extracted. So these are the different steps. So we'll see in each step what we do and how we make the more reliable and manufacturable chip from the ASIC design flow. So here, when we take in deep about this, so specification and design architect. So who will provide this specification? So for example, we wanted to bring one chip to a market. So there will be a customer requirement. So based on the customer requirement, the customer will give the specifications. It has to be worked under this field. It has to work under this particular frequency. The chip size should be like this. So that area, whatever the SOC, everything that will be given from the customer. So based on that, there will be a design architect. So he will fix the how many blocks should come. So what are the blocks or functional blocks to required to implement this particular chip or an SOC. So that is like in this diagram you can see. So this is a SOC. Let us assume this is an SOC. There are a multiple number of modules and blocks in this, correct? So what are the blocks? How these blocks should communicate? All these will be decided by the design architect, and at what frequency these blocks should work, and what should be the total SOC size. That means that area of this particular SOC, and at what power it should work. So that is either it should be a low power or ultra low power. So all those specifications will be provided from the design architect. So once that will be taken at the first stage, in the initial stage, once we have get the system architect, means architecture diagram for the chip RNA SoC. So then the RTL design team will come. So that is the we call in the industry that are called, they are called as RTL design engineers. They will start writing the HDL code, HDL programming. So that is by using Verilog or VHDL program. So that will allows the designer to bring the whatever the architect system architect has given, so into the behavioral model. So of this circuit, instead of defining the internal structures what we have, so they will come up with the behavioral logic. That means that they will write the code. See, for example, we have to design on a 4x1 mux. So we have to write a code, correct? So similarly, so for a design what we wanted to plan, wanted to design, so for that they will write the HDL code. So that is usually in Verilog. So that will be done by the RTL design engineers. So that will be taken care by the at the front end side. And whatever the RTL code which they have written, that has to be verified functionally correct or not. The functionality of that particular code is functioning or not. For example, we have 4x1 mux. Whatever the code which they have written, is it functionally working like in a 4x1? It has to be verified first. That will be done by the design verification team. So synthesis means before synthesis, they will be done by the design verification team, so that the functionality of the code, whatever it has been written by the RTL engineers, will be verified at this one. So that will detect and correct of the design as per the customer requirement. Okay. So these are the just a modular approach. So that means as per the specification we are going. So we'll give the clear architecture. So based on the architecture, we write the HDL design. So that is by using a Verilog or whatever the HDL programming which supports, and then it will be get verified. So at the earlier stages itself, we'll fix the any requirements or any changes to be done at the by design verification method, and so that we'll get we also look for the efficient, means the main focus here is, so we should have better performance, better power, and then it should work at the optimized areas. These are the things it will be taken care by the synthesis team. So that I will show, so that all these can bring up a very good ASIC design into the market. Now let us see, so what steps will come after design verification. So once the design verification is done, it will be given to the synthesis team. The RTL files will be handed over to the synthesis team. So there will be a team called as synthesis team. Usually synthesis will be taken care by the backend team. So that is either by PD engineers or by DFT engineers. That depends on the companies. So usually the PD engineers will take care of synthesis because they will be knowing what kind of technology libraries they should use in the design. So that, so sorry. So that, so what kind of cells to be used to meet the our requirements. That is nothing but to make the more optimized with respect to performance, power, and area. So that will be done by the PD engineers usually. So that is nothing but synthesis, nothing but it is a process of converting your RTL code into gate level netlist. So that means whatever the in the previous slide I showed. So in this way it will be looks like in the RTL design. So RTL files. So it will be get converted into gate level netlist. So each gate to perform that operation, to meet that operation, or to meet the specification, it will be get converted into gate level netlist by using a technology libraries. So the libraries which we use here, it will be done from the full custom team. So that is nothing but analog team. So the standard cells will be provided from them. Those cells we directly use. So only we are telling that it is a semi-custom. We are not designing an, for example, AND gate is required here. We are not designing an AND gate. AND gate it already it will be present in the library. So those will be picked here and then it will be utilized for our design. So that's why it's called as semi-custom. We are not going to do all these from the scratch. So we do it at the gate level. So ASIC design flow is a gate level design. Okay. So the next our main area of interest today's discussion will come. So that is the design for testability. So why we need a design for testability? See, all these are keep going, right? So ASIC design flow is not having, means RTL designer will give the code and then it will be verified by the design verification team and it will go to synthesis and then physical design will take care. Why we need a DFT team here? The mainly DFT team is not involved anything related to the functionality. Actually, the designer, DFT engineer will mainly involved in adding an extra logic which can detect manufacturing defects. So that means that, yes, the RTL team will give, the physical designer will draw the layout, all those things, and then it will give the GDS extraction to the fabrication. During the fabrication, during the manufacturing at the foundry, so there can be some manufacturing defects can occur. So how to identify those, how to detect those? For that, there should be an extra logic inside. So that role will be taken care by DFT engineers. So DFT team, the testing of the chip after manufacturing. So during the design, if you add the logic inside it, then only I can test that chip after manufacturing. So for example, you are constructing in a house, you want an electricity and the plumbing, means water connections. So will you put after the construction of the house or during the construction of the house? So we all plan before the, means get manufactured, right? Before get constructed. So that means we'll plan accordingly where the electricity point should come, where the TV point should come, where the fan should come, where AC should come. All these things will be planned accordingly. Will be put the electric line and as well as plumbing line. Correct. So similarly, to test the chip even after manufacturing, we should have an extra logic inside our design. So then only I can able to control the signals or control our inputs through that channels or that particular path, and then I get to know that my chip is functionally correct or not. Means after manufacturing, is it working fine or not? That will be done by using our design team. So that is called as design for testability. So many of them will be thinking that a design for testability means it is a tester work. No. So the DFT team is totally responsible for design only. So designing, adding an extra logic inside the design, which makes easy to test the chip even after manufacturing. So what kind of defects means during the manufacturing? So there are certain defects can occur that may be shorts or opens or some maybe get broken, all those things. So those chips cannot be placed onto the product directly without testing it. You might have already experienced it in your lab. So if they give an IC to bring up the circuit, there will be an IC tester in your lab, correct? So you will place your IC onto that and then you will press the test. So then it will give okay or not. Means if it is good, it will throw it as a good. If it is not working, then it will show as a bad. So if you don't have that testing option, then using those ICs which are provided from your instructor, you will bring up the circuit. Finally the circuit will not work means, so it is a time waste, right? It is a time waste, and then you'll be stuck in finding what is the fault. Either my circuit is fault or the IC is fault, like that. Before to that itself, if you test it properly by using a tester, so you'll have a confidence that my ICs are working. Where my fault is, you will be able to find easily and then get out of the risk. So that is how even the industry expects before placing our IC onto a product. For example, I am prepared one chip, have designed a chip for mobile. So after placing a mobile and give it to the customer, if the customer is facing a problem, I cannot take it back and then I cannot rectify at that time. Before getting into the market, I should test it properly and then give it to the customer. That is what the intention. For that, we should add an extra logic that will be taken care by a DFT engineer. Okay, so we have so many process under this. So that is scan insertion, memory based. That is, if you have the design as a memories, so then we need to go with memory based, that is memory built-in self-test. And similarly, the another process is called as ATPG, that is automatic test pattern generation. So that are we used to means In deep about all this, I will speak in the next slides. So ATPG simulation. These are the steps we will be undertaking under DFT. So next, when it comes to a physical design, that means that see, you can see here there are flops. All of them are connected just like in a shift registers. So in order to have a controllability and observability. Okay. So next, when it comes to a physical design, so it is converting your gate level netlist or whatever the gate level design we have into physical layout. That will be taken care by the backend team. So that is physical design engineers. They have their own steps to perform to get the GDS output. So that is floor planning, placement, CTS, routing, all those things. So we'll not discuss much about this. That will be taken care by the PD team. Okay, so mainly we concentrate on today's discussion on this DFT area. So that is, let us move on to that. Okay, so as I mentioned you, so what is DFT? The DFT is nothing but design for testability. Have you, all of you are with me? All of you are with me? So have you understood where the DFT role comes in the ASIC design? So after synthesis, we'll get the synthesized netlist. Or at the RTL level also, our engineers will work that are called as DFT RTL engineers. So that means we need to, some of the things will be done at the RTL level and some of the things will be done at the gate level netlist. That I will clarify. Are you all okay now? Are you all comfortable in my means the flow what I am teaching? Are you all following, right? Okay. So I hope all of you are following. So let me continue with the DFT flow. So what is the DFT? So design for testability. So what we need, how do we do this? That is, this is nothing but a technique which is used for detecting the manufacturing defects, which occurs during the manufacturing. So that means that, so as if you don't have any DFT logic, we have to rely more on a design verification team, and it will take a time consuming process. So, and also if you don't have this, we cannot segregate which chips are faulty, which chips are fault free. So that we can't decide. So for that to decide, we should have our DFT logic that will facilitate the design to be faulty or fault free, which will reduces the cost. That means that if you are doing functional team, if every pattern has to be generated, it will take a lot of time. So it will take cost involvement will be more, and it improves the test efficiency. That means that in case of your functional verification, we may miss some of the tests. So we may miss some of the patterns. So as the nowadays the complexity of the chips are increasing, so we need to make sure that the chips are tested properly before placing them into the designs. See, if you are neglecting the test design, means a DFT team now, or if you're not adding a DFT into the logic now with a low cost, then you may need to pay more amount for testing them without DFT logic. For example, you wanted I don't want DFT team to be involved in this design, means for the testing you may need to spend a lot of money with other method. So, or your product may get failed. So with nowadays with no chip is coming out without a DFT logic. So means not only now, so from last 15 to 20 years, so without DFT logic, there are no chips. So chip design. So what we do here is, so this is how the DFT works. So that is, we'll be having a RTL design code. So on the RTL design code, we insert the DFT logic. So DFT test logic, that is nothing but scan. Usually at the two different places, DFT role will come. At the RTL level, we insert some of our components that are like M-based, EDT, BIST logic, and JTAG logic, OCC. All these will be done at the RTL level itself. Once at RTL level it is been completed, then it will comes to a synthesis team. They will synthesize it. That means they convert the RTL into gate level. That gate level netlist will take it as an input, and then we do the scan insertion. Scan insertion is nothing but I will tell you. So that is just stitching all the flip-flops which are there in the design in like a shift registers to have a controllability and observability. Okay, so that will be done at the scan insertion, and that after inserting all this, we need to generate the patterns that will be done by using ATPG, and it will be simulated. So simulation, the patterns will be just generated and it will be observed. If these are means expected and simulated are same, so then it will be okay. If not, we need to that means that there is a bug or there is a manufacturing defect, so that will be detected at the early stage itself. So instead of placing the chip onto the product and then getting to know that it is having a failure, so that will be waste of time and a waste of money, and the lot of uh, remarks will not be good on the product. So it is better to first detect and then make a product. So this without DFT, how do we test the chip? And with DFT, how do we test the chip? So there will not be any access to the internal pins of your design. So it will take a lot of time to test. So that is accessing the internal nodes, detecting defects. It's very difficult. So without having any DFT logic. If you have a DFT logic, then it is easy to detect a manufacturing defects. So there will be a particular process to detect that. So by using a DFT logic. Okay. So it will be improves the product quality. So we can confidently say that my product will work at this stage or up to this means the DFT engineers quality will be measured with respect to the test coverage. So usually in the market, they expect 99% for the stuck-cut coverage, and and 85 to 90% with this TDF means stuck-cut, that is transition delay fault coverage. So all those will give us the confidence that my chip will work very efficiently and very confidently, I can say, and deliver to the market if you have a DFT logic. So high test coverage, so that is faster to test time, means faster test time means we can verify the chip at very less time. So that is the cost effectively compared to other methods. When we have a DFT, we can test it at very high speed, means very high uh, speed. That means with a less time, so that the cost involvement will be less. So early detection. So before placing onto the product itself, we can come to know, so that the yield of the product will be more. So it will mainly to improve the yield of the production. So we go for a DFT. So which will indirectly means which will detect the manufacturing defects which can occur to the manufacturing. Okay. So this is just an introduction to a DFT. So let us see why we need a DFT. So why we need a DFT? So as I mentioned, so many things. So that is detect the manufacturing defects. So which provides a structured way of testing the chips, not like giving this input and taking the output and then verifying only for very small design means we can do that. But when we have a complex designs where we have a millions of transistors, that option is not possible to do manually. So we have some process of doing this testing the ICs by using having a DFT logic in it. So that will give a structured way of testing the IC, so that after manufacturing, so which can detect the manufacturing defects. So that with if you have a DFT in the chip, so that we can bring the chip or a product onto the market on time. The market means, so bringing up the chip or in a product into the market is also a challenging, because so nowadays very competitive. So in this competitive, whoever brings up the chip into the market earlier, so you will gain the market strength, correct? So that market bringing into the market is also one of the things which should concentrate. And reduction of debugging time, so that if you have a proper structured logic inside our design, so that we can reduce the debugging time, so that we can easily find out what is the cause for the failure. So it will increases the test quality. So as I mentioned you, we can confidently tell that my test quality or the chip quality is meeting the this requirements, means meeting the expectation of the customer. So by measuring with respect to test coverage. So reduction of the test cost. So usually the cost will be involved in two parameters. One is test time and test data volume. So that means the test time is nothing but whenever we wanted to test the chip, there is a equipment called as automatic test equipment. So the cost of that equipment will be very, very, very high. So even to test the chip onto the ATM machine for in a seconds or minutes, we need to pay a lot of money. So that if you keep reducing that test time, so then the cost involvement will be high. Means cost involvement will be low. If you increases that test time, so then the cost involvement will be huge. So the main challenging for the test engineer or a DFT engineer is we have to make sure that the test time is low. Test time is low. So that is what we need to do. So these are the benefits of having our DFT logic inside our design, so that it will reduces the test time and cost. It improves us and it assures and it brings the confidence in the designer to deliver the chip to a production or deliver the chip to to place onto the product. So easy maintenance. So that means that even after manufacturing, we can able to test that chip, and if it is fine, then only we can deliver. So we can easily gives a force silicon debug. That means that force silicon validation. Even after get the silicon out, we can test that and then give it to the customer. So ensured it is the productivity, and it is easy to debug when we have a logic inside it. And also most of the things what we do is a structured testing. So in that it will be more of things are automated. So it is test generation or pattern generation, all of these are automated, so that the much of the missing things can be controlled through this earlier detection, early defect detection, so that you can easily identify at the early stages of the production itself, instead of placing them onto the product and then product is getting failed. All these issues will not face. Okay, these are the benefits and why we need to go for an DFT. So let us discuss on the, if we don't have a DFT testing logic, or if you don't have a DFT in the our design, so how do we test? So it has to be taken care by functional team itself. That is called as a functional testing. So that means that, for example, you have an AND gate, two input AND gate. For two input AND gate, how many inputs are required? Means how many combinations are required?
4 combinations.
4 combination, that is 0 0 0 1 1 0 and 1 1, correct? So all of these patterns you have to supply to test that AND gate is functionally working or not, correct? So for in a simple AND gate which has a 2 inputs, we have a 4 patterns, 4 set of inputs, 4 combinations of input. Similarly, in my now the chips are becoming more complex and as it is moving towards the lower technology nodes, the chips are becoming very complex. In that cases, the millions of transistors will be involved, millions of gates will be involved, millions of blobs will be there. So all of them finding manually or finding the faults inside the logic manually, it will be a very, very, very difficult task. So, and also it is a time consuming. So it will obviously it will increases the test time, and also it will increases the test cost. So, and also to store those patterns, that means as I told, to test the 2-bit AND gate itself, we need a 4 combinations. We need to store that. So it requires a memory. So that is test memory. It will increase the test memory. So all these are the disadvantages which we faced. Because of that, DFT has come. So design, we need to generate, we need to test, apply, all these things you have to do manually, or we have to do it with eye care. That means that we have to do it with manually, means so we may missed out something. So that may not gives the assurance that all the defects are been detected. So miss out some of the faults may get missed out of the testing. So that may be possible in case of functional testing. So to avoid all this, we go for to overcome these disadvantages of this functional testing, we go for design for testability. Okay, I hope all of you are clear up to this stage. If you have any concerns or if you have any discussions or any questions, let me know, or else I will move forward by assuming everyone are clear with these concepts. Okay. So as I was telling in the beginning, from the beginning itself, so DFT is used for detecting the manufacturing defects. What are these? What are these defects? From where it occurs? How it occurs? What makes these defects to be occurred? And also because of these defects, how my circuit will get affected or my design will get affected. So in this slide, I would like to explain you that. So the defect is nothing but physical imperfection that happened during the design process. So that means, so during the manufacturing or during the process of bringing up the chip into the from the PAP, so there can be some scratches, or that can be, you all knows how this will works. There are a lot of process involved in making the fabrication of your ICs. So there can be some shorts between the two nets. It's a nanometer technology, right? So these all will be very tiny. So if it is get scratch or small opens or small shorts, all these we cannot be means manually we cannot test them. So there should be some structured testing method. So these defects can occur during the manufacturing. That is nothing but of a physical imperfection that can occur during the manufacturing. So due to that, the fault will get involved in the design. So that is nothing but just a physical representation of that model of the defect is called as fault. So whatever the fault means, I can say it is a scratch and it is a open or it is a short. But the logically, how will we represent? That is nothing but either it is open or it is short. That means short is nothing but it is connected to 0. If it is open means it is connected to 1, I. Correct? So across, you all know that across the short circuit, what is the voltage? Across the short circuit, what is the voltage? Yes? 0, right? Across the open circuit, voltage is maximum. So similarly, we represent here in the same concept. So that is stuck to 0 or stuck to 1. There can be some faults. So that fault will be represented logically. So that is called your fault. Okay. So that means that here, let us assume there is an AND gate. Okay. So AND gate output is stuck to 0. So let us assume this is connected to the ground. Irrespective of your inputs A, B, always output will be 0 only. Correct? This will be faulty. Actually, we should get, if it is 1, 1, then I should get 1. In all other cases, 0. This is the good chip. If you are getting this logic, then I can say that this AND gate is not functional properly. It's not working properly. That means that it is a faulty chip, faulty gate. So that is called as fault. Due to this, the performance will not be same as expected. Correct? So there will be a deviation in its performance of a circuit. So that will gives you failure. Due to the fault, the failure will occur. It means it leads into a failure. So that will not be, you see here, as for the good chip, it should be 1 and here it's 0. So there will not be as per our requirement. The performance will go down or deviation in the performance. So that will be represented, that error or whatever the error output we are getting instead of 1 or in front of that performance failure. So that will be measured by using error. So error means wrong output signal. So instead of unexpected output result, what we are getting, so that is called as your error. The expected was 1. The actual, whatever the simulated or whatever we are getting out of this AND gate was 0. So that is called as error. Okay. So these are the defects and errors related to manufacturing defects. Okay, due to the manufacturing defects, all this impact will happen on our design. Okay, so now to tweak control over this, the DFT logic will be added. What for DFT logic is added is to get the main two things. One is called as controllability and another one is called as observability. What is mean by controllability? You all know that the chips or the designs are very complex. The internal nodes or the nets of in the design is not possible to access directly from the primary inputs, correct? The primary inputs are nothing but from where we are feeding the input, and primary outputs are nothing but from where we are observing the output. It's not so easy. For example, you have only AND gate. Yes, it's easy to find out. If the complex nodes are there, if it is here in this node, there is like two gates which are connected. From the primary input, if you are having only one gate, I can just say, yes, this is 0 or 1 based on your input. But next it has connected to some other gate. Like this, we have a lot of things here. I cannot easily find out what is my output here, right? If you have a lot of signals here or the design here, let us assume there is a lot of combinational logic and sequential logic in between this. I cannot directly control this. What is my output here? I cannot find out that what values I should feed and what values I am getting. So all those things I cannot be able to take the control and observability. That issues to have that. The mainly controllability is nothing but we should have an ability to place or the shift known values to the net or in a node inside the logic or inside your design. That is called as controllability. Similarly, observability is nothing but we should observe. That means that I am forcing their value. That value can be impacted my output or not, that I should get. Means that input, whatever I have applied, due to that input, is my output is changing or not. That value I have to check at the any net or node after we have been given with the known logic, the observability. So it's very simple, just like your electrical switch and bulb is there. No, if we have circuit in the design, I can able to control the bulb from the control switch. If you don't have a switch and a bulb or that circuit itself, if you don't have in the home, how can we do? It's not easy, right? So if you have particular switch from where we can control the bulb, then easily I can on and off I can do. I can change the status from the switch on and off, and I can observe at the bulb it is either glowing or not glowing. If you don't have that option itself, so how do we control that bulb and the switch? It's not possible, right? So that is what we are doing. The DFT is each and every node or a net in the design should be controllable. So means I should be able to place a known value to those nets and observe those values. Then only I can able to find out either it is a faulty or fault free. Correct? There is an AND gate here somewhere. I should have an ability to force these values and observe my what is output. Then I can say that this AND gate is working fine. It is a simple AND gate, means I can do it easily here. But this is placed, this AND gate is placed in a million of transistors or a millions of gates inside the millions of one among the millions of gates. How to take the controllability? It's not so easy, right? Finding that particular gate and then saying that it is a defective. So for that, I need some strategy to make it structured way of testing it this design. So for that, I need to go with DFT logic. Is it clear for everyone? Okay. So to do this activity, we have two different strategies of making the DFT logic inside our design. One is ad testing and another one is structural testing. Okay. So as I was telling you, nowadays the chip size is decreasing. That means that we want a very tiny chips to be get manufactured, and paste onto our products, so that then only our product will become slimmer and smaller and compact one. So as we are moving towards the lower technology nodes to achieve this as decrease in the chip size, so the complexities will increases. So as that means that in the same area we are placing the more number of transistors. So lower technology nodes is nothing but, so we are placing in more number of transistors with a very less number of area, with a very small area. So that complexity obviously increases. So we need to have a particular process to detect these manufacturing defects. For that, we have two methods. One is ad hoc testing and another one is structural testing. In ad hoc testing, that is not, we don't have particular structure to follow. So follow the testing. So that is use the external testing equipment. So we don't have any inbuilt inside that. The test generations are the whatever the patterns we generate to test the logic, it will be manually done. And it is a time consuming process. As it is time to test is more, the cost also will be higher. Okay. So
So what is DUT, sir?
design under test. Design under test. Yeah. So whatever the design which we are taking for the test, that if you wanted to test this, the inputs and outputs has to be observed. So to observe that, there will be a equipment, means that will be done at the external side. So means manually we have to test them. So if it is very small or chips are means the chip size is very small, then we can do it. But so when the millions of cells or millions of logic is placed, then it is very difficult. So then we have to go for the accessing those chips through a particular structure. So then we go for the structural testing. So that means that here uses a chip with DFT logic, and the test patterns are generated automatically. That is called as ATPG. And then as a result of this, the test time will reduces. The cost also will be more effective. Okay. So time to market also we can bring it on time, so that we can give the assurance that our quality of the chip, what we delivered with confidence, that because with confidently we can deliver to the customer to place onto the product, we'll be knowing that up to what level of coverage we have covered. Means inside the logic, for example, we have 100 cells. In out of 100 cells, if you are able to test 99 cells, that itself is a good achievement for a DFT engineer. The one cell, if it is missing because of some constraints, all those things, that is fine. So there will be very less chances that that cell is getting failed, and that is making a faulty chip is very, 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 very less. But achieving 99% of test coverage, itself is a challenge for the DFT engineer. That has to be taken care in a structural way, and there is a methods to do that. That way, if you do, so we can able to achieve.
Sir,
Yeah. Yes.
earlier you told in order to overcome the disadvantages of functional testing, we are going for DFT.
Mhm.
Sir, in ad hoc testing also, we have higher test cost and it is time consuming now, sir.
Correct. So we are not using the ad hoc testing for a testing purpose, for a DFT purpose. We are going only with the structural testing. So ad hoc testing is similar to the functional testing that was taken at the earlier stages and in the initial stages of the DFT when it has come. But now we are not following it. So we go only with structural testing.
Thank you.
So ad hoc testing, these are all the advantages, disadvantages. Disadvantages are more, so we are not going with this. So here skilled DFT engineers are also required, and so many disadvantages. So we are not going with the ad hoc testing. Just I wanted to bring up that. So what are the different testing methods are there? So just I have told you, but we are not going with the ad hoc testing process because it is a more time consuming and also manual efforts are more. Now, when it comes to a structural testing, so here, so we go with a structural testing. Under this, there are a different process. So that is scan compression, ATPG, boundary scan, and BIST. BIST is nothing but built-in self-test. Under that, again, we have MBIST and LBIST. So when you wanted to test the memories separately, so if you have a design with the memories, that has to be tested separately. So that has to be taken care with built-in memory, built-in self-test. So that is memories has to be tested separately. That will be done by using a MBIST process, and LBIST, that is the logical circuits, will be tested by using LBIST. See, the structural testing is nothing but it is to select the test patterns based on the structural information so that we can easily find out the fault. So how do we find this fault? Again, the faults are there are different kinds of fault models. That is stuck faults, translation delay faults, so the bridging faults, IDDQ faults. All of them will be structurally we can able to find it out. So that is we'll be having a design structure details, and then we'll set for the possible fault models, either what kind of fault model we have to target for the design, and then we generate the patterns. Those patterns will be applied on the tester equipment. Then we'll verify that. So if it is correctness, then we'll deliver the chip. So this is as its own structured way to make the chip testable. So advantages here is it improves the coverage and it improves the test efficiency. That means it reduces the test time so that the cost also will decreases. So to do this structural testing, we follow the particular process, that is scan compression, JTAG, boundary scan, BIST. All these are the different process which we need to undergo. So let us now move on to the scan. Before getting into the scan, so let me first briefly explain you how the DFT flow industry follows, what kind of flow for the DFT. See, so design requirements will be given by the customer. So based on that, RTL team will write the RTL code, and again it will gives the RTL files. That is that they also will verify it. RTL team also will verify that whatever the codes they have written is working or not. That by using a spike loss and IJTAG, all those tests will be done, and then it will go to synthesis team. Synthesis team will convert your code into gate level netlist. That means this kind of form will get. This will be called as gate level netlist. That means that whatever the behavior logic which we have written in the RTL, it will get converted into structural logic. That is nothing but gate level. By using gates, it will get converted. Now it will give delivered to the scan insertion team. Scan insertion team, what they do is whatever the normal D flip-flops what we have, all of these will get converted into scannable flops to have controllability. As I mentioned you, the DFT team is mainly looking for taking the controllability and observability. Correct. So to have that, so the gate level netlist will be given to the scan insertion team. The scan insertion team will insert the scan logic. That is nothing but converting your ordinary flip-flops into scannable flip-flops. That will be given to the ATPG team. That is nothing but ATPG is automatic test pattern generation. Those patterns will be simulated, will be given to the ATE machine. Okay, so this is the process we follow in the industry to make the DFT logic inside your IC, inside your design. So what are the tools we use in the industry?
Hi, Satish.
Yes.
I mean, regarding to LBIST, I mean, for a SOC, how
Yes.
much they can target? I mean, percentage wise?
So if we have any memories related, then we'll go with the MBIST. If we have a logic related to the gates, all those things will be targeted with the LBIST. So the
I mean,
percentage, 80 to 90%, we can get the test coverage.
I mean, that is regarding, actually, we had a change, right? Why should
Yes.
they will add this LBIST for, especially for combi logic?
Yeah. When we have other logics, which we other than the sequential elements in the
Okay.
circuit, so those
Okay.
has to be tested, for that we go with the L-based. So that
I
is
mean-
inside the combinational logic. So there can be a logic gates. So
I mean,
all
that
of
can, okay, that can be decided by the RTL guy, DFT RTL guy. Will he'll not-
yes, yes,
Okay.
yes, yes.
Thanks.
Yeah.
Thank you.
So the tools which we use to for the DFT purpose, there are three different main EDA vendors. So in the industry, so that is Synopsys, Cadence, and Mentor Graphics. So for each process, so as I mentioned, there are a different process under DFT. So that is M-based insertion, synthesis. Synthesis usually you can forget it for now because this will be taken care by the PD team. And even we can also do. So in our course, we also cover the synthesis from the DFT team and scan insertion, compression. So scan compression, that is nothing but EDT we call in general term, and then ATPG, pattern generations and pattern simulations. For a particular process, we use a particular tool from the different vendors. For the Synopsys, from the Synopsys, for the M-based, we use SMS, that is store memory system, and the DC compiler, design compiler, we use for the other process like synthesis, scan insertion, and EDT insertion, and Tetramex for pattern generation, and VCS for the simulation. From the Cadence, we use the Genus and Modus and Exilium. So Genus is used for the M-based insertion and scan insertion and EDT insertion. The Modus will be used for the pattern generation, and the Exilium tool will be used for the simulation. That means that to validate the patterns which are generated. And from the Mentor Graphics, we use different tools for the different operations. So that is Tessent M-based we use for the M-based insertion. Synthesis, usually either DC or a Genus. Only two will be used in the industry as I know. So Mentor Graphics is very rarely used. I don't think they use real time. So the Tessent DFT advisor will be used for scan insertion. Test compress will be used for the EDT insertion and also as well as for the ATPG generation. And Questa simulator will be used for verifying the validation, or means to validate the patterns which are generated by using Mentor Graphics. Okay, so let us see each operation what we do. So briefly, so why we need scan and what we do by using scan. So as I mentioned very clearly in the beginning, so DFT is mainly for focusing or getting the controllability and observability, and that means that each and every node inside our internal nodes or internal nets should be able to have a controllability and observability. So if it is a very smaller combinational circuit like this, yes, I can apply the primary inputs and easily I can observe the primary outputs. Just like, for example, full adder, if you take, we have A, B, and carry in, and we'll get sum and carry out. Easily I can apply 8 combinations and I can observe what is the sum and carry output for each combination. So when we have uh, millions of transistors, millions of gates, millions of sequential elements, and if it is a sequential elements, it is not only depends on the present input, it also depends on the previous outputs also. So in those cases, we may not be able to access to the internal nodes directly from the primary inputs, or it will take a lot of cycles to reach those, and then we may miss out some of them. All these issues are there. To overcome that, we need to go for scan. So what we do is, so nowadays, as you all know, that usually the chip complexity is keep increasing as we are moving towards the lower technology nodes. Internal nodes will be fed with lot of primary means a lot of flip-flops which are logically far from our primary inputs, means so we cannot access these pins directly so from the primary inputs. So to have that, these all whatever the flip-flops are there, we will be sequentially connected to solve these problems. So what we do is, so instead of having flops, so we will connect them as a shift registers, just like shift register mode. That means that Q to SI, Q to SI, that in that way we'll connect, so that we'll apply the scan input to each of these flip-flops and observe the output through the scan output. So that clear explanation I'll give in the next slide. So that it will allows us to give the known values through SI to each of these flip-flop and observe that values from the output SO, so that we can have controllability and observability at the each node. So that is what will be propagating, or we will be sending the known values, that is the test or the scan values, test data through scan input, and we'll be observing this test data out through scan output pin. So this is called scan. So how it will works is, the basic principle behind this scan is, we all know that in our design there will be ordinary D flip-flops. Ordinary flip-flop which has D as data input, clock, and Q as a output. So we convert this ordinary normal flip-flop into your scannable flip-flop by adding extra logic, that is called flip-flop multiplexer, 2x1 multiplexer. Extra 2 inputs we are adding apart from this. So when we see here SI, that is scan input, and SE, that is scan enable signal, we are adding extra. So just the D will be connected to the SE is my control input, DFT control signal, which controls between the data and the scan input. For example, if SE is equal to 0, so as we know that the 2x1 mux operation, so if it is select line is equal to 0, the D0 will get connected to the D, means output Q, and similarly D1 will connect it to your Q when SE is equal to 1. So based on this operation, we can have the send my known value to any of the internal nodes through SI path. SI path when SE is equal to 1. When SE is equal to 0, it operates like a normal functional mode. So normal functional mode means whatever the D we are getting, that data only will appear across the D flip-flop input, and that will appears as to the Q based on the clock availability. Correct? The test patterns are applied directly to the internal design by shifting the input values through the serial scan shift registers. So when SE is equal to 0, all the flip-flops like this, if all the flip-flops are connected, SE is equal to 1, so that means it will be in the shift mode. Correct? It will be in the shift mode. That logic also I'll explain. And during the capture, that means when it is becomes 0, so then we are capturing the data from the combinational logic. So other combinational logic we are capturing, so that we can test the chip and we can have the controllability and observability by making use of these scannable flip-flops in our design. So this is how we get, if we means combine all the logic inside. So we have 3 flip-flops I have taken for an example. So we have 3 flip-flops, and which is between the combinational logic. So the functional data pin will be considered as D, and through that means it comes from the combinational logic, any combinational logic. And the scan data will be controlled from the primary input. So this is the input pin for the test DFT engineers. This is created by a DFT engineers. And the port to control between these two, that is D and SI, will be also means SE is the pin which controls. So here little correction mistake is there, so don't consider this. This SE pin has to be connected like here, SE pin, and then all the flip-flops are driving with a clock port. Okay, all the flip-flops are driving with a clock port. When SE is equal to 0, this D data will connected in this way. So you can observe this block color line will be active. This block path. This is called functional path when SE is equal to 0. When SE is equal to 1, this blue color line, whatever this is there, no, SI to Q, SI to Q, SI to Q, this path will get activated. The data will be observed at the S out. This S out and SI and SE are the pins, are the ports which are created by a DFT engineers. See, this is not disturbing any of these functionalities. Here we have a D flip-flop. D flip-flop will act like a D flip-flop only even after adding a extra logic. That is what the main golden rule for us is. We should not disturb the functionality of the design. That as a DFT engineer, we don't have any authority to change or disturb the functionality of the design. Again, the RTL team will come and sit on us. Why you have disturbed my logic? Whatever maybe he has done, we will not disturb his logic. We'll just convert the ordinary flip-flops into scannable flip-flops so that we'll get the controllability. We'll create our own path just to make sure that our signals are passing. Just like in the house, the walls, all those things will be constructed by construction side people. Whereas we will, along with their walls, we'll just add our logic, means our circuit for electricity or plumbing or whatever it is. Similar to that, we are adding it. We are not constructing the house. In the constructed house, we are adding extra pipeline to have electricity or water connections based on our requirements. So similarly here also, we are adding extra logic inside our design so that we'll have a controllability. Wherever we want input to be applied, yes, we can apply. Wherever we want output to be taken, yes, we can take, by choosing the control signal as scan enable. Okay, the clocks will be driving through this clock port. This clock also will be controlled through another from the top port. So that is for the test logic. Whenever it is during the test, the clock signal will be feeding to this clock port will be different, and during the what we call during the functional mode, the clock which will reach us to these flip-flops will be different. Okay, this is what the scan operation is about. So this is how it works. So it works in two different modes. One is normal mode and another one is test mode. So when it is in the normal mode is nothing but functional mode. The functional mode, there will be a one DFT control signal that is called as test mode signal. So that will be 0. So once the test mode signal is 0, then it will operate like a normal functional mode. So it will not be any active, means we are not enabling the test mode. So whereas in the DFT mode or the test mode, again we have two different modes. One is called as shift mode and another one is called as capture mode. That depends on the control signal called as scan enable. Okay, so here in the normal mode, so there is no impact on the scan enable because the entire chip will be in functional mode. So test mode will not be enabled. Once the test mode is enabled, so that means that test mode pin will be there, TM pin. That if it is 1, then we are bringing it to the test mode. Under test mode, we have shift mode. That means where scan enable is equal to high. So you can see here, when the scan enable is equal to high, all of this, the data will be taken from this path, this blue color line. It will be like scan chain. All of these are connected in a chain. That's why it's all the scan cells are connected in a chain. That's why it's called a scan chain. And it acts like a shift register based on the clock positive edge or active edge of the clock detects, then the data will get shifted out. So that will happen during the shift in, and capture is nothing but when SE is equal to 0. When SE is equal to 0, this pin, the data will come from the combinational logic. The data will come from the combinational logic that will be captured. That will be captured by using a capture cycle, and then it will be shifted out again. So shifted out again when SE is equal to 1. So that data, whatever we have captured to these will be get shifted out. So that shift in and shift out will happen when SE is equal to 1, and capture will happen when SE is equal to 0. Okay, this is called as capture window, and this is called as shift in and shift out, that is load unload window. Okay, so what are the advantages of this having a scan? So as I mentioned, it is easy to take controllability and observability. Each and every node in the design can be observable and controllable. Correct? So makes the complete design to a shift register. Just no need to pulse so many clock cycles with a particular one pulse, or based on which mode we select, either shift. Based on that, we can just use the control the shift registers and improve the test efficiency, so that the test time will get reduces, the cost also will get reduces, and we'll get the better coverage, the easy to generate the patterns. So that is by using automatic test pattern generation. That method is there, but disadvantages are here are area overhead. That means that the extra logic we are adding, right? So as I mentioned, that is this multiplexers and the control signals. These are all extra signals we are adding. So due to that, so area will get added. That means extra area will get added. The power consumption also increases, as you know that the number of cells are increasing, so that way may consume some more power, and timing issues may come. So timing issues is nothing but here we have to close the data to reach the particular flip-flop on a particular time. So that due to the mux and all the timing issues, closing we have to take in care, and the routing congestions, as the number of pins are increased in the design, that is nothing but number of wires got increased, nets got increased, that all will may create the congestion routing. Though this will be taken care by the PD and STA engineers. So only the area to meet the area overhead, we are going for the lower technology nodes. Yeah. See, so now, as I mentioned, your scan operation is nothing but we are converting the scannable, means ordinary flip-flops into scannable cells, correct? Scannable cells. What are these scannable cells? So in the industry, we use, there are different scannable cells, scan cells. So that is muxed scan cell, clocked scan cell, and LSSD. That is nothing but level sensitive scan design. The level sensitive scan design scan cell. So these are the different types of scan cells which are available, but in the industry, most commonly used is muxed scan cell. So as I shown here, that is nothing but muxed based. The scan cell, ordinary flip-flop are getting converted into the scan cells by using muxed scan cell. So we have to tell the tool that what kind of scan cell to be used, either muxed scan or clocked scan cell or LSSD. So why we go with the muxed scan is it has its own advantages. So we go with that. So the timing, so means we can meet the timing. So that is, and also the area wise also it has very high advantage, and the scan enable pin is the control pin. So whereas the design means it will be at edge triggered. So edge triggered means it is based out of flip-flop. So it is made out of flip-flop. So the flip-flops are you're knowing flip-flops are edge triggered sequential elements. So it is edge triggered, and area wise also we are having advantage, and timing wise also we are having advantage. The clocked cell is nothing but, in deep about this I will explain you in the next. So clocked cell is nothing but it will be based on the clocks. So that is, so that means, so there requirement of two clocks, one for the clock for the scan data and one for the normal functional data. So that because of that, so one disadvantage is we will not be able to meet the timing. So that is medium, and LSSD is nothing but level sensitive scan design. So that is scan cells. So that is level triggered means which are made up of latches. Okay. So because of advantages and disadvantages, we go with multiplexed flip-flop. So that is nothing but multiplexed scan cells. So here you can see the difference between these three. So this is nothing but your shift flip-flop. To the flip-flop, the D input is connected through a multiplexer which has two inputs. One is test data, test input, and another one is data input. Test inputs comes from the test logic, and data input comes from the functional logic. This will be controlled through your scan enable or test enable. So in this diagram, we call it as test enable. Even if it is scan input, data input, and scan enable, so that is also fine. So only the notations are different, but the functionality wise, it is the same. Whereas in case of clocked scan flip-flop, see, you can observe to this, here D flip-flop means the D flip-flop is directly connected to the D, and the scan input is also directly connected to the D, or means connected to the flip-flop. Only difference is we need two different clocks to control them. So one is, if this clock, CLK clock, if it is active, then the D will propagate. If the scan clock is active, then scan enable will connect it to the Q. So we need two clocks. So on both of these should be controlled from the top. So that synchronization, all those things, timing issues, all those things are not able to control here. So we mainly go with this. Similarly, LSSD is nothing but here also it works with master and slave latches. It works with, means it is a construction of master and slave combination. We have a data. We have a common clock which works on both. It is a common clock from here. The clock is connected to both of these, master and slave. And the scan input pin is applied to a master. And to control this, we have two test clocks. One is for the master test clock is different and slave test clock is different. Again, these two clocks, and again the clocks becomes very high. So as you know that the timing closing is one of the tasks. That means that frequency and time are inversely proportional, correct? If you want a better performance, we should go with higher frequency. If you go with an higher frequency, closing the data on that particular short time is very difficult. So that STA issues will pop up more. So in order to avoid all this, so we go with the mux flip-flops. Okay. In the industry, whatever the designs we use, we are all using with muxed flip-flops, where we are converting ordinary flip-flops into muxed scan cells. So just by adding an extra 2x1 multiplexer. Okay. So where we have a control signal as TE and the test data input as SI or TI, and the data input which comes from the different logic that will be functional data. Okay, this is about the scan. So you have any doubts on the scan? On the scan part? Okay. So by assuming that you are following, so I'm just moving forward. Next, scan compression. So why we need scan compression? Yes, we have got controllability, we have got observability. So then what else we need? See, as I told, scan is nothing but we are making the shift registers in a, means making the scan flops connected like a shift registers. So we have 100 flip-flops. Let us assume 100 flip-flops are there in the design. Yes, we can connect one shift register which is of 100 scan cells length. 100 flip-flops are connected in a one chain. So it's, let us assume one cell is taking 1 millisecond. One cell is taking one pulse cycle, one clock cycle. One clock cycle is of 1 milliseconds. To test that particular chip, that particular chain, how many clock pulses are required? Each flip-flop takes one clock cycle. One clock cycle is nothing but 1 millisecond. Like that, we have 100 flip-flops in a chain. How many? What is the test time? What will be the test time? Yes? Anyone can respond? What will be the test time? 100 flops are there in the chain. Each flop take 1 millisecond. To test that chain, how much time it will take? It is a simple mathematics, right? 100 milliseconds it will take. Correct? So if the tester ATE machine, if they are charging for 1 milliseconds 1 lakh rupees, let us assume 1 lakh rupees they are testing. So that means that how much we need to spend? Yes, 10 million rupees we have to spend on the testing of that particular IC itself, correct? So the designer or the whoever is the client will not be happy with that. So test cost, we have to reduce the test cost. That means that, so I cannot remove the scan cells, right? I cannot remove the scan cells. The only option what we have is we have to reduce somehow the test cost. To reduce the test cost, what I should do? I cannot remove 100 cells. Out of 100 cells, I cannot make only 50 cells to function like 100. I cannot do that. So only thing is I can divide them into a different smaller scan chains. See, here we have a longer scan chain that I will divide it into smaller scan chains. Let us assume let us assume a very simple example, 10 shift registers are there, 10 scan cells are connected in a chain. Instead of 10 in a single chain, I will make 333 or 4, 333 and 4 in a three different chains, so that it will, instead of taking a 10 milliseconds, it will take 3 to 4 milliseconds, correct? 4 milliseconds is the maximum chain length we are having. So within 4 milliseconds, I can test the entire chip or entire design. That is called as compression. See, compression is a technique to reduce the test time and test cost and also test memory of the design. We are dividing the longer scan chains into a smaller scan chains. See, this is the input scan chain. This scan out, scan in, scan out. This we are keeping the same. To make this, some logic is required. That logic is called as scan compression logic. We usually called as EDT logic, because in the testnet, the most commonly used tool for compression is testnet tool. So that is called as compression, means embedded deterministic test, EDT, embedded deterministic test. That name as it has become a brand name. So just like how do we go with, if the product is very good from a particular brand, we call that product itself is with that name, no? So it has become like that. EDT is embedded deterministic test, where we use the testnet tools. That is also a scan compression. Scan compression is nothing but just to reduce the test time or test cost and also test memory. That means the more number of patterns are required if the length is high. Instead of that, we are dividing, and then smaller number of patterns will get generated. So smaller scan chains will be having. It is faster in testing, so we can test it with very less time, so that the test cost also will reduces. Okay, so the advantages here is, so it reduces the test cost, it reduces the test time, and also it reduces the test data volume. That means that the memory required to store those patterns or the whatever the vectors we generate. The only thing is area overhead. That means that extra logic we are adding, no, extra connections we are making. Because of that, so extra logic means extra space it occupies. That will be done by using in the EDT, we have the components are decompressor and compactor. The main components of the compression technique is decompressor and compactor. So that deep we'll study. So in the regular courses, so we'll study what is EDT, how we design EDT. So everything, how to choose the number of channels, how to choose the number of scan chains per channel. So all these things will come, because so here I have shown only one single chain, but in the regular industry, there will be a lot of chains. Like the project which I am handling, it has 2.5 million flip-flops. So all of them I cannot connect in a single chain. I have to divide them into a different controllers. EDT controllers will come. Under EDT, each controller there will be a like 4,000 chains. Under each chain there will be a number of. It all depends on how many number of scan channels we have. Okay, just like that, I cannot means after dividing this longer chain into a smaller chains, I cannot directly bring up that into a top level. Why? Because number of pins available for the test engineers will be limited. I cannot connect all these 3 chains directly from the chip top. Why? Because this number of pins will not be available for me. The designer will tell I will give only 1 pin for sending your scan data in and another pin for taking the scan data out. You do whatever things you want with that. So I don't have any liability to increase this also. So then I should go with this method that is called as scan compression. Okay. So this scan compression will depends on one parameter called as compression ratio. The customer will tell, so what should be its compression ratio for that particular design. So what is this compression ratio is nothing but internal chains by external channels. That means here I told no. So here I told no, these are called as internal chains. These are called as internal chains. These are called as external channels. Means which are connected to a output or input. From where input and outputs are connected, that is called your channels. The internal is nothing but internal chains. These are scan chains. Okay. So internal chains. So these are external channels. The ratio, if you take, that is called as compression ratio. So how many chains we are connecting to each channel, that is called as compression ratio. Okay. So that is compression ratio gives the how many scan channels and how many chains are in the design. So that means how many chains are connected to each channel. That will be measured with a compression ratio. Okay. So for example, let us have one design where we have a 64,800 flip-flops. Means flip-flops. So in the design, these are your sequential elements. Sequential elements, 64,800. So number of scan channels are 6. Let us assume number of scan channels are 6. So internal chains, that means this 64,800 cells are divided into 360 channels. Means 360 chains. How many in each chain will come? Can anyone roughly calculate? 64,800 flip-flops are there in the design. We are dividing them into 360 chains.
180 flops.
180 chain. 180 flip-flops. Yeah. Yes, correct. So 180 flip-flops in each chain will be connected like this, like a shift registers. Out of that 360 chains, I need to connect among these 6 channels. Means I have availability only 6 channels. I have to connect. To connect that, this compression ratio will decide. So means how many chains I need to connect for each channel. That is called as compression ratio. That means 60 chains I need to connect to each channel to achieve this 360 will get connected to this 60, this 6. So compression ratio is 60. So usually in the market, we can go up to 200, compression ratio up to 200. Okay. So usually we try to maintain within 100, but if very complex design, the right now which I worked for 3 nanometer technology, so where we had a huge number of shift registers, so means flip-flops. So they have given us up to 177. We maintained with 177 as a compression ratio. So like this, that depends on the customer. Yes, we can go ahead with different compression ratio. These all will be given by the DFT specifications. There will be a DFT architect. He will provide us what should be the compression ratio, what should be number of channels, chains, all those things will be given. Okay.
I mean, Satish, you are saying for every 60 scan chains, we need a separate EDT, right?
Not a separate EDT. Actually, in the chain, in the one chain, like there can be a number of here we had only one chain, right? Here only one channel we had, right?
Yeah, yeah.
So like this, you will be having a multiple six channels here, which will be
Okay.
connected to the decompressor. All of these six channels, again, it will be connected like this chains, and it connected between internal means external channels. It can have multiple number of external channels. Each EDT can have multiple number of external channels.
That EDT can be shared, or we need to.
Yeah, there will be a controller.
Okay.
There will be a controller. For example, still the number of EDT channels are more, then we go with EDT controllers. For each set of channels, we'll be having one controller that we get with the complex designs. And if still the design is very complex,
Okay.
is still the design is very complex, then we go with SSN technology, that is scan streaming network.
Okay.
Now the advanced concepts in the DFT era is like SSN, that is still EDTs are very high, means more number of EDTs are there, so all of them testing, it will take a lot of time. So to reduce the test time and test data volume, we go with SSN.
Okay.
That is another technology we have to overcome the EDT. EDT means when we have more number of EDTs, we go with SSN.
Okay. Thank you, sir.
Yeah. So, but each EDT can handle more number of external channels with more number of internal chains. But it all depends on if it is out of our limit in the compression ratio, then we go for multiple number of EDTs.
Okay, sir.
So let us assume now we have a 6 channels, and we have more number of here, like 60 is the limited. So let us assume that is 460 or 480 or something. Those numbers I cannot connect with the existing compression ratio. I should go for a 2 EDTs. Like that, we can decide. So this is about compression ratio, which will obviously means decides so how we can connect the external channels with the internal chains. And this is how the compression ratio will help us to bring up the test time and test cost less. So bring down the test time. So that is test time is basically, it depends on the number of patterns and the maximum internal chain length. That is nothing but whatever the chains we have, longest chain length, whatever I take. So as I told, 3, 4, no. So out of 10 flip-flops, if you are connected 3, 3, and 4, the 4 is the longest scan chain length. So that will be taken. And into TCK. TCK is nothing but the time period of the test clock. Time period of the test clock, like 1 millisecond, as I mentioned, 1 millisecond into number of patterns. Number of patterns will depend on so number of flip-flops in the chain. So that will gives you test time. So number of patterns which are required to detect the faults in this. So into the number of maximum length of the scan chain, and TCK is the clock period of the test frequency whatever we use, whatever the test signal whatever we use. And again, obviously the test cost also will depends on the test time. So that is number of patterns, maximum chain length, and so only the difference here is how many scan ports which are available. Means the scan in how many ports are there. So based on that, we can go with because the tester whoever is owning the tester, that is called as ATE machine, testing equipment machine, automatic testing equipment machine. So they will charge based on the how many input requirement for that particular design. Yeah. So based on that, so they will go with this. The cost will obviously depends on the chain length. So as I mentioned, if it is 10 flip-flops in each chain, yes, the cost will be more. If you divided them into 3, 3, and 4, the cost will reduce it to 4 flip-flop, means 4 flip-flop chain. Whatever the maximum chain length, now it got to 4. So for that, cost will get reduced. Okay. So this is
so the scan chain length will be the number of flip-flops in the
Yes.
chains.
Yes. Number of flip-flops which we connect, no, like a scan
Yes.
chains. So SI to Q path, SI to Q path. So based on that, how many numbers of flip-flops are connected in each chain, that will gives the scan chain length.
Okay, thank you.
Yeah. So now let us move on to the ATPG. So the ATPG is nothing but, yes, we have inserted and we have connected them in a different scan chains. But how to validate these connections are proper or not? As I mentioned, so we have to test them. So to test that, so we need a patterns. So as we discussed in the beginning, so if it is two input AND gate, we need 4 combinations, that is 0 0 0 1 and 1 0 and 1 1, to check it's functionally working as a AND gate. So similarly, 1 minute. So ATPG, why we need ATPG is, in order to validate whatever the insertions we have done, we need to validate by generating the patterns. So we cannot generate patterns manually, right? So as the design is very complex, see here, so we have here 2 inputs. Yes, I can give all the 4 different combinations here, and I can just check what is my output. I can say that it is working like in a NAND gate. But the as the chip complexity increases, the more number of inputs, internal nodes, all those things has to be considered. So for that, we have to generate the patterns by using we have to automate this process for generation of the patterns. That process is called as automatic test pattern generation. So the procedure which involves the generation of input patterns that can assert your presence or absence of the faults at the some locations. For example, that pattern should tell us there is a fault or there is no fault. That means that if we are getting as we expected, then there is no fault. If we are getting a different from as we expected, then there will be a fault. As we have an NAND gate here, if you give 0 0, if you're getting 0 as an output, so then that means that there is a fault in this, correct? If you're giving 1 1, then output if you are getting as a 0, so then there is no fault, correct? NAND gate operation. So that will be find means that we can able to find by generating the patterns, correct? So we can able to, by applying the patterns across these inputs, to find out what is my output. Based on that, I can predict either it is faulty or fault free. So for that, to make these patterns generated automatically by using a DFT tool, that is called as ATPG, automatic test pattern generation. Automatic test pattern generation. Okay. So now, so there are test patterns. There are different types of test patterns. So usually in the industry, we use deterministic test pattern generation, exhaustive test pattern generation, and random test pattern generations are very rarely used. So exhaustive test pattern generation is nothing but all possible inputs. As I mentioned, for 2 input means all the four combinations we give. No. So similarly, for example, you have here four inputs means all 16 combinations we have to give. So in general, if you have a 2 inputs, then 2 to the power of n patterns are needed. So all of them generating and giving manually, it's a lot of time consuming process. Due to that, we go for will not go with the exhaustive test pattern generation. The next one is the random test pattern generation. So that means here it is not following any particular sequence of inputs to be applied. It will just randomly take some inputs just randomly it will take some inputs and it will generate, it will try to generate, means it will try to find out the defect. For example, we have out of 16, right? 16 combinations if we have a 4 inputs. But all the 16 combinations it will not do. Randomly it will pick one. It will try to find either a fault is there or not for this particular pattern. It will keep repeating this process until it is not finding any faults. Until it is not finding any faults. So that process it will be done by using random ATPG, means random test pattern generation. Deterministic is nothing but here we have targeted patterns for generating to achieve the high fault coverage. That means that based on the fault locations, we give the inputs where I need to find the fault. For example, here I need to find the fault. What pattern I should give to the A and B. That will be determined and that pattern will be applied. That is called a deterministic pattern. This is the most effective and it will give a better coverage. What we do in ATPG is we'll be having a design that is inserted with the scan, and we apply ATPG tool to generate the patterns that will detect the fault. Okay, so this is how the method we follow here. Okay, so the next is that is what I explained you, exhaustive test pattern generation. The exhaustive test pattern generation technique which implies that applying the input combinations and checking just like it is functional testing only, correct? So all combinations we need to apply and we need to check one by one. So if you have a n inputs, it will take 2 to the power of n input combinations. So you may not be able to apply every pattern, right? We may miss sometimes. So exhaustive testing is not used in regular ATPG because it is time consuming process. Okay. So when it comes to the random pattern generation, as I mentioned you, so here it will take a LFSR, that is nothing but randomly it will generate, that is linear feedback shift register. Based on that, it will keep generating the patterns and apply onto the our device or the design. It will same process will keep repeating until there is no new faults are being detected. Means it will generate one pattern. Let us assume 0, 0, 0, 0. For that, some patterns are generated. Means some faults are detected. It will continue, and again it will go for the some random like 1, 1, 0, 0. Let us assume 1, 1, 0, 0. It applies. It finds some other faults. Again, it will go with some other logic. That is like let us assume 1, 0, 1, 0. It will apply. For that, if there is no faults are detected, it will stop. Like that, it will keep repeating. But so some faults may go undetected. In this random pattern generation is nothing but, so it may not detect all the faults in the design. So that is a disadvantage of this. But advantage here is very less number of patterns we get. That is one advantage. But some faults may go undetected. All n number of faults will not be detected through this. So that's why, so we'll not go with random pattern generation also. So the one which we use in the industry now is deterministic test pattern generation. So here the procedure which follows is particular fault, means it will target for a particular fault. So the patterns will get generated to detect a particular fault. For example, you have here one gate. Here I need to find a fault. For example, I need to find out a stuck at 0 or stuck at 1 here. For that, I need to send some pattern here to make sure that this fault will be get detected. Particular fault in the design. To do this, it follows some method that is called as sensitization. Sensitization means we should identify where I need to means for this, I need to, for example, I need to detect this fault. I need to make sure that this fault will get sensitized, means it will get activated. That fault should propagate, means I should make sure that how this fault should be observed at the output. Means opposite value, means some value I should apply here so that this fault will appear across this. That is what is called as propagation and justification. So after applying these values, I need to verify it from the backtracing, whatever my applied pattern has detected correct fault or not. That is called as justification. Okay. In this deterministic, we have two methods. One is symbolic difference and another one is path sensitization. Mainly we use path sensitization. We will not go with symbolic difference. That is based on the Shannon's expression, but we will not concentrate much on this. We directly go with path sensitization. So that we uses the three different process. It follows three different processes. That is sensitization, propagation, and justification. Okay. Path sensitization. So as I mentioned, path sensitization is mainly based on the particular fault to be detected. So our particular location. So it is general should up. Is it correct? If apply opposite value, if that value appears across this, then that means that there is no fault here. If still I am applying 1 year, but still it is coming 0, means that means that there is a stuck 0 fault. Correct? Are you getting my point? For example, there is a fault site here which is stuck to 0. This net is stuck to 0, connected to ground. So instead of applying a 0, if I apply 0, there is no use. Correct? Here also is 0, only 0 will appear. So I think that there is no fault. But what I should apply here to find out this 0 means I should apply 1. That means opposite value I should apply. If I apply 1 here, still 0 if it is coming as any input to this gate, that means that there is a fault here. In that way, we have to activate the fault. We need to activate the fault by applying the opposite value to the fault or a net. Fault on the net. Okay. So next step is, once that fault is selected, that fault we should make sure that it should propagate to the next gate, or it should reach the primary output, because everywhere we cannot take output and then check, right? So it will be observed at the primary output. To observe the primary output, I should make sure that the fault is propagating. See, there is stuck to 0. I applied 1. That 1 has not come here. This 0 should propagate, means I should apply here what value? 1, right? I should, if I apply 0 again, so there is no use. If I apply 1 here, if there is no 1, I am applying 1, 1. These are 1, 1. Actually, you should get a output as 1, but I am getting 0. That means that the fault is propagating. Are you getting my point? Here, AND gate is there. AND gate. So if I apply 1, the opposite value I have applied 1, and this, due to this stuck to 0, you will get 0 as output. That means that this fault which was here, it has propagated to here. Like this, we should make sure that it should reach the primary output. So from there, we can trace back to the inputs to justify that the fault is, means output is fault or free, or this detect means this device is fault, or means it is fault from free from the fault or faulty. Based on that, we can take a decision. So like that, the patterns will get generated. So based on the primary output, we can decide either it is faulty or fault free. This
Sir,
is
I
how,
have a question.
yeah. Yeah, please.
Sir, so the faults are identified using structural testing now, sir.
Yes.
We detect the faults using structural testing, and when we know the faults in random test pattern, like even though we know the number of faults, some faults will not be identified, is what you're saying, sir?
Yeah, because in the
test pattern
random pattern generation, we are not going with one by one. So randomly, it is been the patterns are generated.
Generating test
means
patterns.
pattern. Yeah, correct. So it may target all the faults in the design or may not. So we are not assuring that it is fault based. Means, for example, it may create one patterns to determine the fault at this location. At the same time, it may lose the fault at this point.
Okay.
That pattern, whatever it is randomly generating, that may target for this fault, but in the circuit, it may lose some other faults. So we are covering all the faults in the design. So that assurance we are not getting. So because of that, we are not going with that.
So for
Yeah.
all cases, we are going ahead with deterministic test pattern generation only, sir.
Correct. This is a
Okay,
method
sir.
which is the most used method in the industry.
Okay, sir.
So that
Thank
is
you.
how we do is by following these three process. One is sensitization, that is nothing but activating the fault and propagating that fault to the primary output, and then justifying that either it is a fault or fault free based on the output.
Okay, sir.
Okay, so this is how the method we use for detecting the faults through the ATPG. So which mainly uses D algorithm. So that is D algorithm to find the faults. Okay, it works based on the D algorithm. Okay, so this is more accurate method of detecting the faults, so that we can confidently get whatever the coverage we can able to meet. Means if we are meeting the coverage as per the customer requirement, we can confidently tell that it has targeted all the different faults. Next is what kind of faults we can target, or what kind of faults we can determine by using DFT logic. So there are different faults, different fault models. It may occurs during the manufacturing. So that means that fault model is nothing but something that could go wrong in the construction or manufacturing during the manufacturing, or detect the design defect, or due to that the device will go as a failure, or the design becomes failure. Correct. The good fault model should satisfy the two criteria. That means that it should able to reflect the behavior of that defect. Whatever the model which we choose, we should able to identify that defect, correct? And it should computationally efficient, means it should be able to generate the and behavior of that particular fault should be get detected using pattern generation and simulation. So there are four different fault models: stuck-cut fault model, bridging fault model, delay fault model, and IDDQ fault model. So we mainly concentrate on stuck-cut fault model and delay fault model. Okay, stuck-cut, what is the stuck-cut fault model is nothing but, so the line or a node or any net or any inside the circuit or inside the design, if it is connected to 0 or connected to 1, that means that either it connected to VDD or VSS. So you know that VDD is nothing but it will be having high voltage. That means high voltage means like positive voltage, and VSS or ground, if it is connected to ground, that will be considered as 0. And if it is connected to VDD or VCC, that will be considered as 1. Okay, so that is called as stuck-cut faults at any node, either input nodes or output nodes, anywhere in the design. If it is get stuck to 0 or stuck to 1. We call stuck at 0 or stuck at 1. So stuck at 0 means it is connected to 0. Stuck at 1 means it is connected to VDD. Okay. Similarly, the bridging fault is nothing but it is bridging between the two inputs or two nets. Means short between two nets or two inputs, that will be called as bridging faults. And the delay faults are nothing but the delay occurs in means more than the expected propagation delay. So you all know that there will be a propagation delay over each gate. So if it is more than the expected, then that will be considered as delay faults. Under delay faults, we have two different types. One is called as transition delay faults and another one is path delay faults. That I will take up when we deeply discussing about delay fault models. But IDDQ is nothing but abnormal IQ set. That is nothing but the current is drawn from the circuit. That is excess current. If it is drawn, that will be related to the IDDQ faults. But in our training and as well as in the industry, they mainly concentrate on stuck at faults and transition delay faults. So with these two, we can able to say that the chips or the designs will be fault free by targeting these two fault models. So now let us.
Satish.
Yeah.
Yeah, I mean, whatever the test patterns we are generating, separately we will generate a stuck-at faults, separately we will generate, and whatever transition faults and the path delay faults we will generate separately.
Yes. We have a
I
method.
mean, okay, yeah, tell.
Yeah, we have a separate methods and separate switches to enable the tool to generate the patterns under stuck-at and under transition. So we'll say that what kind of pattern means what kind of faults to be targeted to the tool.
I mean, those, I mean, separate, I mean, during testing also, I mean, during the testing at AT also, we are doing separately these models, right? I
Yes,
mean,
we deliver, yes, correct. We deliver the patterns separately, both for stuck-at separately and at speed separately. At speed is nothing but transition delay faults. So separately we'll generate and separately we'll deliver to the ATE. Even ATE team also will test them separately for stuck-at separately and transition faults separately.
I mean, for the transition faults, whatever the STA team will close all the timing, right? You need to take any file from them that whatever.
SDF, correct. Yes. Oh. SDF files we have to take from them. So that is means after generating. Usually how it goes is as a DFT engineer, we'll deliver the scan inserted netlist to the PD team. So they will do the placement, routing, all those things, and then they will give the PNR netlist to us. And the meantime, they will also deliver to the STA team. Yes. So STA team will be responsible for closing all the timing issues, and they will give us the SDC and SDF files. So based on that SDF files, we have to simulate it. That is called as timing simulations. Those patterns only will be delivered to the ATE to test them with that particular timing constraints.
I mean, whatever they are giving constraint for you, right, for generating of transition faults, yes. They will give separately SD, I mean, scan mode separately and functional mode separately. How they will give?
Yes. They will give in a different modes. One is functional mode, another one is DFT mode. So again, in the DFT mode for MBIST, based on the customer requirements, they will give different SDCs. Okay. For MBIST separate SDC and for scan mode separate, and again in that slow capture separate and fast capture separate, like that they will give the SDC files.
One doubt will be there. In generally, after tape out that test, we need to test a chip, right? Correct. First, you guys will do SAF, right? Stuck-at faults, right? Correct. After that only we will go to remain. Yeah.
Correct. First, we do stuck-at faults so that then only we can check that at a lower frequency. So all these means the design is okay and connectivity checks are all fine. So then we go with at speed means high frequency testing.
Oh, thanks, sir. Thanks.
May I know your name?
Narendra.
Yeah, Narendra. Yeah, this is how we do. Yeah. So with At speed will come later. First we go with stuck at.
Yeah.
Next let us see how the stuck models will be helping us to find out the defects in the circuit. So that is, which is mainly to detect, so either primary across primary inputs or primary outputs, if it is get stuck to 0 or 1. So that will be observed, means, so whenever we have a method, means whenever we wanted to find a stuck faults at any internal nodes, directly we cannot find it at the primary input or primary output. So we should activate it with by sending them with an opposite values, and then we should make the fault to be propagated to the primary output. So then only we can able to find it out. So either it's we can give the justification, either it is a faulty or fault free. So with that method, we can able to find out either it's stuck to 0 or stuck to 1. So stuck at 0 example, if you take, so irrespective of whatever the inputs we are giving to that particular point, the output will be always 0. So here we are applying the normal signal only, but as it has y is stuck to 0, so we'll always get the y as 0 irrespective of 0 or 1. Okay. So similarly here in this case it is stuck to 1. So irrespective of the signals, whatever we are applying across this gate or whatever output we are getting across this, but this y is connected to 1, always it will be 1 only. So to detect this, what I should do is, what is the opposite value I should apply here to make sure that here I should get a 0. That means 0 0 0 1 and 1 0 can able to detect the fault across this. All these three combinations can able to detect. Whereas if it is stuck to 0 means only 1 1 I should apply here, then only I can able to detect this value. If it is stuck to 0, if I apply 1 1, if supposed to be output as 1, but if you are getting 0, so then I make sure I can assume that there is a stuck at 0 fault. That I need to propagate based on the other signal, means other branch or whatever other logic how it is connected. So this is how we go with finding the stuck at faults. So mainly we concentrate on finding the stuck 0 and stuck 1 across all the nodes or nets in the design. So next was delay fault model. So delay fault model, we have two different types. That is the, as it is mentions, I told you that this delay is exceeding the means expected propagation delay. So whatever the delay we are getting more than the expected delay of the propagation, so that will comes under delay faults. It can occur in two different ways. One is transition delay faults and another one is path delay faults. Transition delay faults means across each gate. So there will be a transition delay faults. So in either at the input or outputs, changing from 0 to 1 or 1 to 0. So there will be a delay. So more than the expected, if it comes, then that will comes under transition delay faults. So actually it should be like 1 means 1 or 0 means. So it should be starts from 0, exactly it will go to 1 and then 1 to 0 when it comes. So exactly at that point. But as we know that there will be a small delay for rise time and then fall time. So due to that, the transition delay will occur. So time from input transition to output transition. So that if it is more than the expected, then it comes under the class of transition delays. So similarly, the cumulative sum of the many gates or the many delays will comes as a path delay. So that is cumulative delay along that particular path, or that will be considered. So this will helps to find out a false path or multi-cycle path, all those things. Based on that, we can choose whichever the path which has less delay, that will be set it for the propagation, means sending across. If not, we'll make it as a false path. So these two different fault models will be targeting mainly. So other IDDQ and bridging faults will not concentrate much, but so those are also required. So under ATPG, these are the concepts which we wanted to see now. So in the real time means in the training, we also do different for fault coverage analysis, all those things we'll do. So, but in the demo, I have not covered that one. So mainly in the ATPG, what are the DRCs we face and what are the challenges means the mainly the test coverage. So why we get the low test coverage, how to improve that main concepts we will be covering. So that is most important. And next is after generating the patterns, we need to validate them. So the that is simulation step. So simulation process will take. So whatever the patterns we generated out of this from the ATPG, that is either for the different faults, either for the stuck cut or for the TDF, it has to be validated. So this is before delivering to the ATE machine. So we ourselves has to be validated. So either whichever is correct or not. Means based on this one only, they can segregate either the chips are fault or chips are uh, fault free. So if our patterns itself, if it is not proper, so then it will be difficult for them to segregate either the chips are which chips are faulty, which chips are fault free. So it may go some good chips also under a faulty category. So in order to make sure that, so we should first simulate them under simulator. If all those patterns are passing, then we can deliver to the ATM machine so that they can apply those patterns to their real silicon, and then they can segregate the chips, which will compare your actual patterns. Okay, so under this, so we mainly concentrate on that is fault simulations. So fault serial simulation, or under fault simulations, we have serial simulation and parallel simulation. So we have to do in the simulation means parallel simulation and serial simulation. We have to again we do for the chain testing and as well as for the scan testing. So what we do in the chain test is, so which is mainly responsible for making the interconnects are clean. So that means that it acts like in a shift register. So only in the shifting cycle, and it will be done at the low frequency. So that means that scan in to scan out. So all the shift registers will be connected like SI to Q path. So that connectivity will be checked. Whatever the patterns we apply, so is same as our expected or not will be checked in the chain test. So all the scan chains are properly connected or not, that will be checked through our scan chain patterns. To generate this in the ATPG, we have a particular switches. So those chain patterns will be generated separately. For again in the chain test, we have serial patterns and parallel patterns. So you know that serial patterns are nothing but the will be applied one by one. So that is serial patterns, either it may be a chain patterns or scan patterns, which will be applied one by one to check the output response of your circuit. So whereas in case of parallel simulations, either chain patterns or scan patterns, which will be applied all the patterns will be applied parallelly to these scan chains across each scan chain, and it requires very means only one clock pulse to get the response out, because for each flip-flop will be applied with our inputs in case of parallel. Whereas in case of serial, whatever the length we have, that many number of clock pulses are required. For example, we have 10 scan cells in a scan chain, that many number of clock cycles are required, and one for the capture, and again for the shifting out we need another 10 cycles. Totally we required as many means length of the scan chains, a scan chain whatever it is there, that plus capture cycle, and then we have to get the loading and unloading cycles also. So whereas in case of parallel, usually for the simulations, parallel patterns will not be delivered to the ATE. This is just for make sure that these patterns are passing from the our side. So as we all know that at the ATE machine, there will be a limited number of pins to apply the patterns. So only the serial patterns will be delivered to the ATE machine. So both chain test and as well as for the scan test. Scan test is nothing but in the capture cycle, we'll be taking the data from the combinational logic. So first, what we do, so during the shift, we'll be testing at the low frequency. So the shifting operations will happen just like shift registers. And again, during SE is equal to 0, we supply a high frequency signal. That is nothing but that control will be done by using OCC, that is on clock controller, on chip clock controller. Inside our design itself will be having a clock controller, which clock to be propagated during the SE is equal to 1 and during SE is equal to 0, what clock to be propagated, that all will be decided by OCC. Based on that, we are going to capture the data from the combi logic, and then that will be shifted out through the when S is equal to 1 again. And again, the shifting operations will be done at the lower frequency and the capture operation will be done at speed frequency. To do that operation, we call it as scan test. Scan test, or we call it as capture patterns. These are called as capture patterns. These are called as chain patterns. Okay, so why we will not go for high frequency during the shift is nothing but there will be a lot of switching actions, so that may create heat dissipation. So to avoid that heat dissipation or switching actions, we go with lower frequency. So these are the different simulation types. And again, so as Narendra was discussing, so yeah, Narendra, here we do zero delay simulations and as well as timing simulations. So for timing simulations, to do the timing simulations, we need SDF files. So on which corner we need to run. So either with lower frequency, means either worst case or best case. So based on that, we need to do the timing simulations. For that, SDF file is required. So that will be taken from the STA team. So zero delay means we will not consider any delay. So zero delay without having any consideration of timings. So we'll just check for the data patterns are passing through the design properly without annotating any delays. That will be done. So or it will gives the confidence on our netlist is proper and the design is proper, so that we can go for the timing simulations. So to check whatever the patterns which we have delivered, which we have generated with at speed, those patterns will be used here for simulations. For the zero delay, we can use the stuck-cut patterns itself, but whereas for timing simulations, we have to go with TDF patterns, a transition delay for patterns which we have generated with by considering that for which case we are doing, either for the minimum means min corner or max corner. So what are the mismatches it may get, or what are the possible failures you may see during the simulations? So in the simulations, basically we see mismatches that are called as binary mismatches and X mismatches. So what is the X mismatches is nothing but we are getting the expected, and what we're doing is in the simulation is we are comparing the results with expected and simulated. Expected result and simulated result both are same, then the miscompares will not be there. If there is any change between the expected and simulated, so there will be a miscompares or mismatches. So the possible mismatches which occurs in the real time is X mismatches and binary mismatches. X mismatches means we are expecting 0 or 1, but the actual simulated is X. The output is don't care. So means we are not unknown value. So we are not knowing that value. So that case is called as binary X mismatch. But another case is binary mismatch. So there, if you are having 0 as expected and 1 is the simulated, so opposite value. So expected was 0, simulated is 1. So similarly, expected is 1 and simulated is 0. That category is called as binary mismatch. Okay. So that may occurs because of so many issues. So that may be timing issues. For example, if we have some delays and setup and hold violations may occur. So all of this are related to the timing violations. And library mismatches. So let us assume, so there are there will be a different libraries which we use at the different stages for synthesis and the scan insertion and ATPG and simulations. The libraries what we use during the insertion, same libraries we should also use at the simulations also. If there is any mismatches, the cell which we used for the insertion is different and the cell on which the patterns we are applying is different. So that mismatches may come. So when we miss to read the proper libraries, so that comes under the category of these are all generally what mismatches may get during the simulation. That is what I am telling, but it is varies case to case. And the real time, whatever the issues we come or whatever the issues it comes, those issues we need to solve. And other cases is design rules violations. That means that during the insertion, if we have some warnings, that may also create some mismatches during the simulations. Some errors we might have made it them as warnings, or we might have ignored during the insertion. Those also may create some mismatches during your simulations. And the real design issues also may come, so that are because of some shorts or some opens may occur during in the design itself. Some unconnected nets or some opens or some means which are not solved during the insertion may also pop up during the simulations. So simulations is more important before delivering to the patterns to the ATM machine. If you all solve these and patterns are passing, so then we can confidently give it to the machine, ATM machine, to check with the patterns with the real silicon. And clock rule violations. That means that some of the times whatever the clocks which we supposed to be defined may not be properly propagating to the particular clocks. So that due to that also, or some maybe getting clocked or gated due to some other logic. In those cases also we'll get clock violations. That also may leads into mismatches. And binary and input means bidirectional input and outputs. So that will be a bidirectional buffers, tri-state buffers we call. So due to that also, if the particular enable signals of those, if it is not active, so that also will leads into bus contention violations. All these may leads into mismatches. So this is all about the technical part of our discussion. So if you have any doubts related to this, let me know. So another half an hour I'll take non-technical related things. So where we get the opportunities and what are the opportunities we have, what are the skill sets we should have. So all those things I will take up. So you have any doubts till now technically, so you can ask me.
Satish, what is the duration of this course? And
yeah, this course duration is 6 to 8 months. I will just come to that schedule part of it.
okay.
Yeah. I will explain.
What the tools and what assignments you are doing, that one also I show you.
Yeah, I will cover everything.
Okay.
Yeah.
Thanks.
Yeah, I will go ahead with that. Yeah. So as you all know, you're all background of ECE and EEE branches, maybe means electrical sciences. So some of them may be aware about the DFT and some of them may not be aware about the DFT and what opportunities we have in the VLSI field for the DFT, why we need to go for DFT training. So as we all know, that is in the market, there is very high demand for the DFT, means VLSI engineers, especially in that. So when we go for a lower technology nodes, the technology, as we are moving towards the lower technology nodes, the complexity of the designs are increasing. So the requirement for solving the DFT challenges are increasing. The skilled DFT engineers available right now in the market with proper DFT skill set are less. So many companies are having a shortage of talent shortage with not only at the product-based companies, even at service-based companies also. Like Intel, AMD, Qualcomm, all of them are keep hunting for the skill set which is matching with their requirements. And also, once if you get into the DFT, you no need to look back again for changing the any domains. So you can have a stable growth. So in the long-term stable growth in the career. So this is a high market and demand what we have for the DFT. And critical skill set development. So once if you gain and if you keep updating yourself to the industry requirements, yes, again your sustainability will be more. And the high salaries. So as far as I know, so in the market, the pay for the RTL engineers and DFT engineers is more as compared to others. And also the trained candidates in the DFT will be less, but the requirements are more as of now. So this will means we are not only restricted to one particular area, either into front end or back end. So we have different places to work, start from RTL to post silicon. So even at RTL level, we do the insertions like EDT, OCC, and other IJ tag. All these insertions will be done at the RTL stage. That will come in the front end. And again, after synthesis, we do the scan insertion, ATPG, and simulation. That part will come again at the at the after synthesis. Again, the silicon will get fabricated and it has to be validated before sending it to the market. So post silicon team, again, if my silicon is failing on the ATE machine, that debug issues, we need to solve that issues also. So there also we have an opportunity. So overall, if I say there will be 2 to 3 places in the ASIC design flow, we can contribute ourselves. So that is as a DFT engineer. So hands-on tool experience. So everything we need to do with the hands-on by using different tool. So that is, as I mentioned, there are 3 different vendors: Synopsys, Decent, and Cadence. In our training center, we have Cadence as a main tool. We are authorized partners of Cadence, and also we are trying to get the Decent tools. So these are the fundamental requirements means what are the skill set we should have to grab the opportunities which are there in the market. So that is, we should know so DFT methodologies and techniques, that is scan architecture and insertion, how to insert. We should know the pattern generation, ATPG pattern generation, and M-based boundary scan, test compression, that is scan compression, what I told. And we should have validate all of these. Whatever the insertions we do, we have to generate the patterns and we have to validate them by doing the simulations. And to the basic things which we should know is basics of DFT and HDL. If you are familiar with Verilog basics, then it is good. And ASIC design flow. These are the basic concepts we should know. Yeah. So you should be familiar with tool handling, that is DFT tools. So from the different vendors, we have a different tools. So maybe some of them are common, but the comments what we use are totally different. But the concept wise, it is same. The comment from the Decent may not be matching with the comments what we use for the Synopsys. So that comfortability you have to see. But when we have a fundamental strong and the basic DFT concepts are strong, whatever maybe the tools they give, we can work on. So that is not a big issue, because the flow will change from one vendor, one company to another company, or one client to another client. We can't depend on the same tool or same flow which we will be working. Because now, for example, if I take TI Texas Instruments, they use completely cadence tools. If I take Intel, they use only Tessent. But some other companies, they use mix of both. So like that, there are different requirements. So, but we should be familiar with the tools, whatever the tools you are working on. Yeah, automation. So next is automation scripting. So because we have to tell the tool what things to be done, that is through comments, so that the tool can understand tickle comments. So we should be good at tickle scripting. So we also cover that advanced level of tickle scripting in our training. Yeah, if it is next emerging trends in DFT is how to integrate AI and ML for testing and debugging and reducing the test time, and as well as debugging issues faster. That helps us to make our task completion easier. So how to make automated scripting, so that by using either any of the scripting languages, by either by Tickle or by Python, or how to integrate these ML or AI and ML into our design. I mean, test about design for testability will be the next trending areas in the DFT. So we are, as you all know, that we are VLSI Minds. So the team, we are all working here. From all of us are working in industry, and we are dedicated to transfer the aspiring engineers into industry professionals, or whatever the programs which we are planning, which includes both front end and back end. So yeah, so we use industry standard tools, that is EDA tools. So all our experts, our trainers are from industry, and completely it will be a practical based learning. So more or less, so whatever the essentials which are required, only those will be a theoretical classes, and the remaining all will be hands-on, and will also provide placement assistance and assurance. So this is a vision and mission of our training institute. We mainly focus on innovation, research, and global competency, so to become global leadership. And we also have a lot of collaborations with service-based companies to bring up some of the industry standards into our learning experience. So we also collaborated with service-based companies for placement activities. So mainly we provide in 4 different domains, that is design for verification, testability, and analog layout and physical design. So I will be the main trainer for design for testability. Yeah. So this is the schedule, and means this is how the outlook of our DFT course goes. So it is a 6 to 8 months course. In that, so we'll be covering 2 months as a basic. We categorize as a DFT basics and DFT main course. So on the DFT basics, we starts with GVim and Linux. These are the main essentials which are required for any engineer to work in the VLSI domain. So you must know the editor tool, so that is GVim, and you must know the Windows to operate, that is Linux platform. So, and after that we'll be covering with advanced digital, that like FSMs, all those things will be covered. Advanced digital concepts will be covered, and mainly we need a tickle comments to make the flow automated. So more automation scripting is required. So advanced tickle will be done. That means it will start from the basics, but whoever is still beginning the career now, they can also catch, and even it will be helpful for the industry who are industry professionals also. The CMOS basics and whatever the concepts which are required for with respect to DFT will be taught here, and the basics of Verilog, because as we know that we are not concentrating much on the functional concepts of the design. So we are main goal is to detect the manufacturing defects. We are not having much requirements to know that how it works, but at least we should know the how what is that? Means what it is, or structure of the netlist, all those things. To know that, so Verilog basics which are needed for the DFT will be taught. So this we are estimating that it may take 2 months, and the main course will starts with DFT basic concepts, scan insertion, and test compression, ATPG simulations, and fault coverage analysis, and what are the DRCs we face, even in scan insertion and during ATPG, and mismatches what we can get. So all those things will be covered at this line. And the more advanced topics which we are planning to cover is JTAG and MBIST, and also OCC and ETT insertions. All these things will be covered at the chip top level. And the projects what we are planning is 2 different levels. One is at the block level and another one is at the chip top level. So here 3 to 4 blocks will be combined together and to make the chip top. So when it comes to fees and other supports, yes. So as of now, we are planning for 55,000 plus GST. So if any early registrations comes, we can give a 5,000 of discount, and we give 24/7 tool access. So tool usage you can access at any time, and one-to-one mentorship. So there we have a trained mentors with us. So they will connect with you for any assistance you require, and recorded videos will be available for all the sessions, both for training, means both for main DFT and as well as for the mentor sessions. And every month there will be an assessments. So whatever your learnings are in line with our training model or not, so that will be assessed. So if there is any deviations, that will be corrected. And the mock interviews, so which we need to before facing the interviews with the companies, you will be undergone with for each module there will be a mock interviews, so that you will gain the confidence to attend the real-time interviews. So interview preparation sessions will be taken. So here we'll give all the questions, expected questions, which will be during the interviews. Because as we are working in industry, we know that what will be the expectation for the fresher level, and as well as those who are having a industry experience. Up to that level, we'll train you, and full-time placement support. So until you get placed, we'll take all the responsibilities. Yeah. So this is the contact information. For any queries, you can contact. This is my number, and this is the admin number. You can contact at any time. Yeah, what are the opportunities we have? So you might be having in your mindset after getting trained. So DFT trained freshers, where and all we can apply, where and all we can get. Yeah, a lot of opportunities are there. As I mentioned, there is a high demand career for the DFT. So as because we are moving towards the lower technology nodes like 3 nanometer, 2 nanometer, and 5 nanometer. Right now, I'm working with a project which is 3 nanometer technology. So I know what are the challenges we are facing, and as we are moving towards the complex SoCs. Yes, without DFT, we can't chip out or we can't tape out any chips. So as it is a mandatory skill, so which is required. So now we know that AI is integrating part of our life. So AI accelerators and AI applications, AI chips are all coming. So because when you wanted to use AI applications, there should be AI supporting devices also. So the devices without AI integration, where we'll use AI applications. So there will be a lot of demand. So I recommend DFT as one of the career means high demand career growth we have in the VLSI domain. And career opportunities for DFT freshers. If you do see in the industry, there are a lot of roles we can play. So as a freshers, if you start your career may start with a ATPG engineer. So that is nothing but ATPG and simulations is the skill set they will give for the freshers. And later on, you can also move to the scan, and then you can go for the MBIST, and then you can go for the chip level. So this will be the chip level activities and ATPG activities and scan activities and MBIST activities. So usually the MBIST engineers will be exclusively doing the MBIST operations, and scan operations will be done. Scan, ATPG and simulations will be usually the task which will be everyone will be getting. But as I got opportunity to work on both, because I work for NSS Electronics, they take end to end. So starting from MBIST to delivering the patterns to the ATE up to their have a exposure, so that I can make sure that all these skills will be get transferred to our trainees. So for silicon validation also is another area where we can get the opportunities. But as the freshers, I am recommending, so there will be a lot of opportunities for ATPG and simulation works. Yeah, skill set required. I have already mentioned you a lot of things. I have spoke about this. These are the things which we need to have. And what are the companies we may, because someone may not be having idea about what are the semiconductor companies where we can get the job opportunities. These are the some product based companies and very few service based companies I have mentioned. There are a lot more here. That is all Quest Global and InSemi Technologies, and lot more are there. Accenture, Amazon, all of them are now. So Amazon I have mentioned, no, Amazon, Google, all of them are semiconductor companies only. So the companies which provides the EDA tools for us to work on, so that are Synopsys, Cadence, and Siemens. These are the main three EDA partners for all other companies who provides tools to perform a DFT task. So how our career growth will happen when we enter into the industry? So usually, so it all based on the company to company. Usually they take it as trainee engineers, and then if it is already a trained, so then you can start with a junior DFT engineer level, or they will also give a DFT engineer. So directly, if they are already having a MTech and all those things, directly they start with a DFT engineer, then senior DFT engineer, lead engineer, senior lead engineer, and again DFT manager and senior managers, like that. It will growth will go. And is this is just a rough estimation I had put, very low numbers. So in the industry for DFT engineers, 5 to 6 lakhs into your experience is the expected salary. So it also go up based on your skill set, and where you are located and which company, and based on the company in which you are working, and project demand also. Very low, and very everyone can expect with this number, but usually 5 to 6 lakhs into your experience. Maybe in the beginning you may not be reaching up to that level. Once you reach the 2 years of experience, definitely you can expect 5 into your experience. Yeah, how we have to prepare. So you have to prepare in this means, like, you have to concentrate on all the practical learnings. You have to do how to use the tools efficiently, and you have to work on your own projects. All this will guide. So if you this is about from my side, and this is the some news related to VLSI opportunities. We may having a lot of doubts in that. So after doing a training, will we get the job or not? So how India, means government of India, is taking a lot of initiatives to bring up semiconductor manufacturing up into India. So meanwhile, we'll also get a lot of direct and indirect employment, right? So they are planning for a lot of things. That is 1.2 million by 2020, means 2032. So no need to wait up to that time. The opportunities may come at any time, but we should have that skill set, right? So when it comes, we don't know, you don't know, but when it comes, we should be ready to grab those opportunities. I recommend you to get skilled. So opportunities may hit at any time. Nobody knows when the opportunities comes, right? So even now I am in the industry, every day they will keep messaging in the LinkedIn and sending requests for the change in the opportunities and looking for the trained means experienced candidates. But meantime, so they also get the trained freshers and who are in the working professionals also. These are the news which I got very recently, because our mindset was like you may be from premier colleges, but some of the students may be thinking that, so we are not from the tier 1 or tier 2 colleges, but the industry or VLS industry looks for only tier 1, tier 2 institutions. Like that, they will be having a mindset, but not this, not like that. In reality, they're also liking, means taking from the all the colleges levels, but their skill set should match. There are a lot of projects which are taken care by Government of India across all the different states. So already some of them are ongoing, some of them are in progress. Yes. So if you have any doubts related to this today's demonstration, I would like to answer all of them. Yeah, if anybody is having any doubts, let me know. Any questions to me in the chat? Yeah, okay. Apart from these answers, I don't see any questions. Yes, if you have any doubts related to this, let me know. So I will take up the questions. I'll just stop sharing, but I'll be online. Yeah. Yeah, any questions? May I know just introduction of each one of you so that I will have a proper understanding. Either your, yeah, Batulu Narendra. Can I start with?
Yeah, Satish. I had experience in other domain. Okay. This I need to explore DFT, so that's why I need to train.
Okay, okay, yeah, good. So already you are working professional, Narendra?
Yes, yes, I am working professional. I had around 10 plus years of experience.
Oh, very nice to know. In the VLSI domain?
Yes, 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 correct.
Oh, very nice to know, Narendra. Yeah, may I know which domain you are working right now?
I mean, synth, ST, and PD. Three.
Oh, synth, STA, and PDA. Very nice to know. So STA and synth is a part, means will be
Yeah, that's
moving
why
in between them. Yeah,
I am daily we are I'm communicating to DFT guys.
correct,
So
correct,
some
correct.
terminology, some understanding.
Yes.
So actually, I need to start career in DFT only. At that time, I did not get chance.
Okay.
So now I am saying.
Very nice, Narendra, to know that uh, you're looking for a day of the opportunities. Yeah. Akshir, Akshira, Akshari, may I know your just a small introduction about yourself? And also one more thing I would like to just tell you that we are not taking a bulk enrollments also. We are restricting only 15 to 20 enrollments so that we can give individual attention for each one. So that is what our aim is. So 10 to 15 or 15 to 20 is the max. Yeah. Vaidehi Reddy, may I know your introductions? Like, hello? Okay. Hello? Yeah, if you have any doubts to me, you can ask any questions to me. You can ask. I hope many of them are. Anybody is willing to introduce yourself? Yes, you can just give your introduction, or else I'll take up questions. Tirumalesh, I hope you are unmuted. Yeah.
My name is Vaidehi.
Ah,
Just now I have completed my BTech.
okay. Okay. You are in ECE background.
Yeah, I'm from ECE background.
Yeah. So nice, Vaidehi. You have taken a good decision to join DFT. Yes.
Thank you.
A lot of opportunities are there, so you can just make yourself skilled. So definitely opportunities will come. Yeah.
Thank
Tirumalesh,
you.
hello. Okay, I think you are not audible if you are unmuted or. Okay, thank you everyone for your time and attending this session. So if you have any doubts, you can reach out to us, and If you have any, if you wanted to know the enrollment process, you can contact our admin. Okay, no issues, Ramesh. Yeah, okay. Thank you. Akshari Kondapalli, if you are okay to introduce, or else it's okay, no problem. Yeah, thank you, everyone. You can be in touch with our admin or myself. So I have just, if you want, I can post my number also. Yeah, I can post my number also here. Yeah. Yes, you can. We are planning to start these sessions, regular sessions, from 30th of this month, May 30th. So before to that, if you could able to do the registrations, so that will be good for us. Yeah. Thank you, everyone.
Yeah, thank you.
Thank you for your patience learning. It's almost 3. So I hope you by interest you are there in the call. Oh, thank you very much. Thank you,
Hello,
everyone.
Chetan.
We'll wind up for. Yes, please.
Uh,
Gopika, please.
how many days will the recording sessions be available?
For 1 month it will be available, but as I recommend, you should go through within 1 week, because you have to catch up our flow, right?
Yes,
So
yes.
if it is, yeah, the recorded sessions will be available, but only thing is, I recommend you to, for example, you wanted to come for a offline, means online class in the next week. If you are knowing the before classes, it will be good, so that if you are keeping a regular way, if you are finishing the task, it will be good.
Okay, Chetan. Thanks.
Yeah.
Hello.
Yes, Ramesh.
Hi, Satish. Yeah, sorry, my PC had some permission restrictions, so I
No
joined via.
problem.
Yeah,
No problem.
yeah. So a bit of my background. So I'm in the VLSI domain for the past 11 years now,
Oh, very nice.
and so I've been previously working on the ATE domain, post silicon
Hmm.
validation side,
Hmm.
and few years ago, like I think around 4 years ago, I transitioned into analog mixed signal DFT.
Okay.
I'm
Like
more on
unlock.
the,
Okay.
yeah, I work on the IJTag tool chains, decent
Hmm.
IJTag. I
Mm-hmm.
wanted to check more on the digital side as well.
Oh, nice to know, Ramesh. Yeah, this is a good opportunity for you, and also you are there in more than 1 decade, means you will be knowing in and out of all the opportunities which are available. It's good to know. We
Yeah,
can work on
I,
that based on your means we can go advance also. So based on your requirements, you may, means in the basic things you may not be, you already will be comfortable, I hope.
yeah,
Yeah, up to advanced level also we can take up, no problem.
yeah, it was a great presentation, Satish. Thanks for that. Yeah.
Yeah, thank you, Timkesh. If everything is fine, we can wind up for today's. Yeah, thank you. Thank you all. Thank you, everyone. Once again. Have a nice weekend.
Thank you. Bye.
Thank you. Bye bye.